Design is the next phase. We're going to look at constructing clean geometry from a conceptualized design. In the design phase, the faceted geometry is used to construct clean geometry that can then be used downstream. The process used to construct the geometry will depend on the final production method, low or high volume. The design phase can be divided into two parts. Reconstruct the faceted geometry using the selected design, and then refine and optimize the design if needed. In the following demo, we will reconstruct the faceted geometry 3 ways to support low to high volume manufacturing. The priority in low volume manufacturing is rapid turnaround. The first method shown in the demo supports low production volume using freestyle design to quickly create a refined version of the geometry, keeping the theme of the design while providing cleanup to create a smooth representation of the geometry. The priority in high volume manufacturing is quality and manufacturability. The second method shown supports high volume production using freestyle design to model the geometry that can be machined using 3 or 5-axis machining. The third method also supports high volume production. Traditional CAD construction techniques are used to support NC machining or die casting. Let's take a look at the demo.
This video shows the process to reconstruct clean geometry from the generative design faceted results. The first step is to publish the faceted body. This will allow us to create a clean model that does not contain carryover geometry from the generative design output. Once published, a new model is created, and the faceted information is copied into the model. The faceted geometry will serve as a reference during the reconstruction process, providing a 3D visual overlay. Once the faceted geometry is copied, we are ready to begin the reconstruction process using core modeling functionality in Creo. To support and manage the reconstruction process, we will create a design exploration session to manage and store checkpoints for the different design scenarios representing both low and high volume production models. The first step is to close the existing model and create a new design exploration session. In addition to storing checkpoints, design exploration provides flexibility during the reconstruction process. If not satisfied with changes, the user can simply select a defined checkpoint and revert back to that version of the model. This provides a degree of flexibility when exploring different design scenarios and options. When the model is opened, the pre-modified checkpoint is automatically created. For low volume production, the need is to simply create a clean version of the geometry for 3D printing. This is easily accomplished using freestyle design to manipulate a primitive shape by pulling and dragging vertices, faces, and edges. The tool allows a user to rapidly manipulate and generate high-quality surface geometry using the faceted model as reference data to define the shape and contour of the model. The 3D dragger makes it easy to modify and refine the shape of reconstructed geometry. Freestyle design is like having a virtual clay model to design freeform and stylized geometry. The overall goal for low volume production is to capture the theme of the geometry while providing refinement to improve surface quality and improve design aesthetics. At any time during the design process, the user can create checkpoints to capture the status of the model. Checkpoints are used to capture the history and evolution of the design process. To finish the video, let's close the current session and retrieve the final design exploration session. Checkpoints 1 through 10 capture the evolution of the low volume production model using freestyle design to create a clean version of geometry for 3D printing. Checkpoints 11 through 14 capture a more refined version of the model to support high volume production using 5-axis milling. Checkpoint 22 is a reconstruction of the geometry to support high-volume production using die casting or 3 and 5-axis machining.
This part of the design phase will demonstrate refining and optimizing the design. Creo Simulation Live runs within design exploration and provides immediate feedback during the reverse engineering process. Using design exploration provides the complete history and evolution of reconstruction. CSL is used to provide guidance for refinement and optimization of the geometry throughout this part of the process. Using CSL gives a design direction, enabling you to make modifications which reduce the maximum stress on the part. Since the modifications are targeted at the high-stress areas, over-engineering is eliminated and cost is reduced. The demo will show how quickly the part can be optimized.
This video shows how Creo Simulation Live is used during the reverse engineering process to support model refinement and optimization. To start, let's first open the design exploration session and review the reconstructed geometry to support low and high volume production requirements. Checkpoints 1 through 10 show the evolution of the low volume production model. The model was rapidly reverse engineered in freestyle design to create a clean version of the faceted results from generative design. Reviewing the checkpoints shows the design progression and the approach using freestyle design. Although very complex, the organic shape is easily captured using fast, intuitive manipulation of the geometry. Checkpoint 10, Refine Shape, is the final version of the model. From a purely visual standpoint, the design looks acceptable. We could stop here, but why not use CSL to support the validation, refinement, and optimization of the design? Given the speed and ease of use of CSL, we can easily perform the analysis and make improvements to the design. The simulation has already been defined and saved with the checkpoint. The only thing needed is to select Live Simulation and the Simulate icon. The fringe plot shows the model stress. Selecting the icon will identify the location of minimum and maximum stress on the model. Let's now look at checkpoint 14 to review the stress in the high production model. The area of high stress is located on the main beam. Using CSL results to guide us, let's modify the freestyle geometry and see if we can lower the stress. We can easily hide the generative results and make some modifications to the freestyle feature. If we increase the material near the location of stress, there is a good chance we can reduce the stress. To do this, let's modify the geometry by selecting the edge and defining the direction to drag along the main beam. Selecting Complete will regenerate the geometry and reveal the results. This rapid design change resulted in a 6% stress reduction in the model. Updating the checkpoint will save the changes. Let's now open checkpoint 22 to review and validate the second high production model we reverse engineered using core Creo functionality to create a prismatic parameter-driven design. Using CSL, we can quickly analyze and identify the area of high stress. This model has a higher stress than the previous model, but a similar location of maximum stress on the main beam. To reduce the stress, we will need to modify the main beam geometry by editing the graph that is used to control the shape and height of the beam section. A datum graph is a powerful design feature that can be used to vary section dimensions when using a variable section sweep. By adjusting the curve, we can modify the sweep profile and add material to the beam. Selecting complete regenerates the model and updates the analysis results. The area of high stress is shifted to a new location, and the high stress has been reduced by 15% with this change. Our refinement and optimization is complete at this time. To finish, we'll update to checkpoints and save the design exploration session and apply the current status to the Creo Parametric session. The next step in the process is to perform final validation on the model using Creo ANSYS simulation.
Let's check your knowledge. Select all that apply to Creo Simulation Live. Creo Simulation Live provides a design direction, eliminates over-engineering, reduces costs, and runs within design exploration. The analysis phase will now validate the design.